Should work good. Right, good morning, everybody. Today we're going to talk about some stereochem and fun stuff about E2 reactions in general. We're going to see predominantly these are going to be, of the four reactions that we have learned, E2 is the most useful. And so we're going to spend most of our time on that. So remember, we have four kind of reactions. These ones are a little bit, I don't want to say completely useless, but they're kind of. There are certain situations in which these are the best ones to use because they use the easiest reagents. And so if you're trying to do something really simple and you've got a nice tertiary substrate, these can be useful. But typically they're not. Because of the fact that they go through the carbocations. So because they go through carbocation intermediates, you have the option for all sorts of rearrangements. You have hydride shifts, methide shifts, ring expansions, all sorts of weird stuff that can happen because of your carbocations. Because they're unstable, they want to migrate to make themselves more stable. SN2 is pretty good, but we find that it's um, less commonly used. Because it requires it only substitutes something, right? So odds I'm over here. Yeah, that's right. Um, these kind of they substitute something. So they will take one kind of usually good morning, Monica. Usually a kind of a leaving group, right? And they'll replace it with a nucleophile. And you'll end up inverting your stereochemistry and all that good stuff. So kind of useful, but we're going to see that E2 reactions are going to be the most useful of all of these because these make alkenes, and they're very reliable reactions if you have the conditions that need to be met with these. So alkenes, as we're going to see, are going to be very useful. We're going to have, I think, 14 different reactions we're going to do with alkenes. Isn't that fun? Um, it'll be interesting. So we're going to see that functionally E2 is going to be your kind of best bet out of these four for in terms of like their utility in synthesis, which is really what it is. So because once you have that alkene, you can then turn it into an alcohol if you want. You can move things to the other side. You can move things to different carbons. SN2, you have to want your new substituent where the old one was. But if you make an alkene, we're going to see you can then move substituents around to different places. So E2 is going to be our most useful, so we're going to spend most of our time talking about that. Let's think about E2. This is a concerted reaction. We are going to lose a beta hydrogen along with our leaving group, and we make the alkene. So, for example, depending what base we use, we're going to end up with multiple products here. all of these things. Let's say we use, let's say we're going to use, I don't know, sodium ethoxide as our base, and we heat it up. So remember, heat is always a good thing to help with this. If we don't use a bulky base, we're going to end up with both the Hofmann and Zaitsev products. And note in this case, we also have some stereoisomerism. We have a cis alkene and a trans alkene that can be made. We're going to see that we have, this is our Hofmann here. Probably in this case will be our least common product. We're going to have our trans Zaitsev and our cis Zaitsev. Remember, I'm only using cis here in kind of just terminology, helping you see the relationship between the substituents. And it's pretty obvious for us here, cis and trans, right? Remember, with naming things, we use E and Z instead. But this is just showing you just more easily. So we end up with three products here. We have the Hofmann product, we have the trans Zaitsev product, and the cis Zaitsev product. Okay, there we go. We're going to see that probably our number one product will be this one. This will be the predominant product here. This will be the next one, and then the Hofmann will be our third product. So in terms of like how much we make, so maybe we make 50% of the trans Zaitsev, we make 30% cis, and then 20% Hofmann or something. Just making these numbers up, but that would probably be your kind of ratio of the products you make. So we have some ways to do this. Remember that we can get the Hofmann if we use a bulky base. We can get Hofmann exclusively. And so that's why I kind of introduced the reaction using bulky bases, because in OChem, while chances exist for multiple products to be formed, we want our reactions to be as specific as possible. So if there's a way we can exclusively get one product over the others, that's generally a better way to do it. So typically we use a nice bulky base on this, and we'll only get our Hofmann product. So remember some bulky bases like triethylamine. We have the dimethylpyridine. Oops. T-butoxide. This, oops, this monstrosity. I guess the tri. I don't even know, one diethyl propoxide. I don't know, something like that. These are all real bulky bases. We've got a lot of carbons on them. We've got lone pairs that can be acting as our bases. These will typically give us the Hofmann product because they're so bulky. So that's one way to kind of control this. Remember that the other kind of important bit of this is that we must have an anti-periplanar beta hydrogen for this to work. And so we're going to see that sometimes we don't have that. We're going to see that, for example, if we have something like this, and we try and put in our bulky base, we get no reaction. However, if you did E1 on this, you'd also have a, well, no, E1, you'd do weird things. So if you tried to do E1 instead, This would be an E2 reaction. You could get this to react E1. How might that happen? You'd lose your bromine, you'd have a carbocation then in the middle. You'd have a methyl shift. You'd end up losing your bromine, you'd have a methyl shift. Do, 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 do. Cut our carbocation there now. And then we can eliminate in all sorts of weird ways, depending on what base we use. We could get, I'm going to just go down or whatever, we could get a whole mess of things. This is again why E1 reactions are not as good. But in this case, this substrate can only undergo E1. So we'll end up with two products here. Probably we're going to end up with this one more, depending on what the base is. This will be the more substituted alkene. This is your Zaitsev product. This is your Hoffman. With E1, depending on what we used, we use methanol and sodium methoxide, we're probably going to end up getting this dude far more than the Hoffman one. So with E1, we're going to get a whole mess of stuff. But that's probably what you'll get with E1. With E2, you won't get any reaction there. So it depends what conditions you use. So remember, E2 requires the presence of a beta hydrogen, so a hydrogen 1 carbon away to your leaving group. So next to this carbon, we have the dark blue carbons. Those dark blue carbons have no hydrogen, so therefore no E2 reaction will take place. It doesn't necessarily have to be something crazy like this. We could have another case that wouldn't give us any reaction. If we did this, if we tried again E2 on this, if we tried to do our T-butoxide and heat, tried to do this as E2, again, we're going to see no reaction here. The reason is we don't have, even though we do have hydrogens, we have, in fact, a hydrogen on either side. These can't be anti-periplanar. So we're going to see that E2 reactions, they're very nice reactions, but sometimes you just can't have them happen. So you must have an anti-periplanar hydrogen. With this, if we take a look at this, cyclohexane, and we kind of look at it as a chair, I'm going to just start with we've got our methyl group here, we've got our chlorine, and then we have our other methyl group, which is here. So you can nicely make them all equatorial and happy. But the problem is the leaving group needs to be it has to be equatorial, as does the beta hydrogen. So if we do a chair flip on this, to the less likely form, if we do that, we have now our methyl group, or I'll say chlorine. No, it's going to be our methyl group. Our chlorine is pointing up, and our methyl group is pointing down. Notice here our hydrogens are equatorial to this chlorine. They're not anti-periplanar, they're on the same side. So we're going to see that that's why we don't get any reaction. if we want to look at this in terms of a double Newman projection, we can do that. I'm going to go ahead and let's look at these two. Actually, let me look at this one so we can see the chlorine more clearly. So if we look at these two bonds as a double Newman, our favorite, that's the H. Got a methyl group pointing down back there, H pointing up. See, on this one we have methyl group down, hydrogen up, and the rest are just hydrogens. So if we look at what's anti here, remember that we saw we could do Newman projections for our E2 reactions to see which where the hydrogen and leaving group need to be. Here we have not hydrogen as anti-periplanar to our group. If we had the chlorine on an equatorial position, there's no way we can in fact get an anti-periplanar hydrogen. Because if we just take a look at a double Newman where chlorine is, I'm going to just draw a new molecule, it doesn't really matter. This is just showing you, oops. Okay, if we look at this particular conformation, again, this one would not be able to react until it flips. So we're going to see the stereochemistry is going to be very important for us here because as drawn, the chlorine has to be axial for this to happen. And we have to have a hydrogen in the other axial position. So here we have chlorine axial, but there's a methyl group on the other side. So no reaction. Here we have chlorine equatorial, so no reaction. I mean, this will flip and react, but right now, if you just try to do this, we're not going to get it to work. We need this to be, we need this thing to be up here. Now we can say, aha, here comes our triethylamine, goes in and does the reaction, and we end up with our cyclohexene. So without those methyl groups there, we still need to make sure that our chlorine would be axial. So there's a lot to consider with these. So first off, you need to have a hydrogen to begin with. Secondly, you need to be able to have your leaving group in an axial position. Another way that we might encounter problems, I'm going to actually draw this way. With cyclohexanes, these tend to be a little more obvious. That's why I'm focusing on them right now. And it kind of helps tell us why we could only do certain things, right? This one will also give us no reaction. With our base. Why is that? We have plenty of hydrogens, and look, one of them is anti-periplanar. It's right here. Those dash hydrogens are anti-periplanar, so what's the problem? Again, lies in the chair. If we redraw this molecule, If that chlorine is going to be axial, that means we need to have we need to also have two T-butyls to be axial, exactly. So, not going to happen. So we saw that even methyl cyclohexane is like 95% equatorial methyl group. Putting a T-butyl on, let alone two, there's no way we're going to get those to be axial. And so we're not going to have a reaction there. So if you remember, we talked about kind of relationships. If we had cis 1,3, they would have to both be axial or both equatorial. Normally, this thing is going to hang out as equatorial. Not even normally, 100% of the time, this thing must be hanging out equatorially. So, in order to eliminate, though, it needs to be axial. So, because that can't happen, this is the way that the molecule is going to hang out as 100% this, 0% that. No way it's going to happen. Constituents are too large. Absolutely. So there's so much to consider with these reactions. Even things that are multiple carbons away can still affect your things. So with this, we see that we do need to have our leaving group to be axial. So if you have other things preventing it from becoming axial, then that's a problem. However, if you have things that help it become axial, and you have beta hydrogens, like if we had those T-butyls on dashes, it would be very easy to react this, because the chlorine would have to be axial, and the T-butyls would be equatorial. And so, lots to consider here. All right. So, questions so far on this? A couple things that will make this reaction not happen. No hydrogens to begin with. Uh, no anti-periplanar hydrogens. Or just kind of the inability to rotate yourself so that you can get this reaction to happen. So remember that molecules, just if they're all single bonds, can rotate just fine. If you have double bonds, though, or rings, they add rigidity to your structure. Rings cannot rotate. They can flip, but they can't rotate. And so flipping puts different restrictions into play. Because normally, if you've got chlorine and you've got some T-butyls around on a regular just chain, whatever, it'll just rotate and now poof, you've got your chlorine ready to go. But this ring here has new restrictions on it. If we had just a plain old boop 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 boop, this will react just fine. No problem. Because we can just rotate things. It's no problem. If we have all these things 3 carbons away. No problem at all. We just say, aha, well, we'll rotate our molecule. Here, let's say we've got hydrogens on edges and dashes. We'll just rotate this thing. If we rotate that carbon, say now we have our chlorine behind it, just rotating. Now we have an anti-periplanar arrangement, just rotating that carbon around. So remember, undrawn, we had these things. So if I just rotate it, I'm going to rotate it, I guess, that way, this way. I'm rotating it clockwise if I'm staring at, forget it, I'm not going to try and explain it. I'm just going to rotate it. If I rotate it, I see very clearly I have an anti-periplanar hydrogen, and now we can have our base come in, kick out our leaving group, and the hydrogen. No problem. Who cares about those two T-butyls all the way over there? Not a problem. But in rings, that could be a problem. So with the rings we saw with those T-butyl groups nearby, prevent us from getting axial. On the q-axis, absolutely, of course, why didn't I think about that? Yes, it is very clearly the q-axis we're rotating on. Very good. So, yes, it'll be good. All right, and then so once we do that, ta-da, we end up with our product. All right, let's look at a couple examples from the book here. So, yeah, let's do this one. Where would be like this? Okay. And let's use triethylamine. Who cares? Some bulky base, some heat. These help your. Actually, we probably don't need a really bulky base on this one. Whatever, we're just going to use it anyway. Probably is going to be less reactive if we use a bulkier base. So if we just use here, we'll say we'll use trimethyl ammonia instead. So a slightly smaller base. So, anyways, just any old base. That's not the point here. What we want to look at here is the hydrogens. That's the part that's interesting to us here. So, remember with these, we need to have anti-periplanar hydrogens, right? If we look here, we have no hydrogens on that beta carbon, but we do have a hydrogen here on that beta carbon. So that's the one that's going to be reacting. And so we're going to need to make sure that we rotate our molecule such that we have the chlorine and hydrogen on the opposite sides. So whether those mean they're both in the plane, whether that means they are going to be both one on a wedge, one on a dash, whichever. We can do it as a Newman as well. And I think that's honestly the easiest way to do it, but we can do it in wedge dash, and then we'll look at the Newman. We're going to see that if we try to rotate this, we can rotate either carbon. We can rotate this green one around this way, or we could rotate that one around, either way. I'm going to rotate the one on the right because I feel like it. So I'm going to leave my chlorine here on this wedge. So I want my hydrogen to be on the dash, on the next carbon, right? So if I do that, if I rotate it such that the hydrogen is on a dash, I'm taking that, I'm looking at the hydrogen, I need to rotate it counterclockwise so that it goes backwards. As a result, our ethyl group is going to come out to the front, and our methyl group is going to become the one that's in the plane. So we're going to have now our methyl group here, and our ethyl group will be up there on the wedge. So just rotating everything around. I would suggest models for this. Models will help. Here comes our base. Now that we have these rotated anti to each other, I'm going to have that come out. And so we're going to see that in our product, notice that these two groups are trans to each other. They're trans to each other here, and they're going to be trans to each other in the product. So we make our double bond. There it is. We've got our T-butyl. Our ethyl group stays there. And our methyl group, which was trans to the T-butyl group, stays trans to the T-butyl group. Notice that you may not see that directly from the molecule that we started with. So it's important that you rotate it so you can see what the relationships are to each other. So that methyl group and the T-butyl group are trans to each other in our kind of transition state. Once we have rotated so we see what's going to be reacting, then we can see how it's going to relate to each other. So these two are still trans to each other. Again, I'm just using that word trans to talk about the relationship. This is not a trans alkene. This is definitely a Z alkene because the ethyl group has priority over the methyl group, right? It has more carbons, so it's got a higher atomic number. So, but these two are still trans to each other. Again, that word to describe their relationship, not about the alkene, but about those two substituents. If we draw this as Newman, it may become a little more obvious. If I draw this as a Newman projection, I've got my T-butyl group pointing up, and so I should be a good chemist and say T-butyl because that's what we use for Newmans. I've got my chlorine on a wedge, hydrogen on a dash. If we take a look at our original molecule, we have hydrogen on a wedge up there. We have a methyl group on a dash, and the ethyl group down. So this is the original molecule. And so if we need that chlorine to go bye-bye, no. Zusammen is the one when they're on the same side. Entgegen is the opposite one. E-alkenes have our biggest things trans to each other. We don't really care about bulkiness. We talk about priority, right? So if we assign priority, we look at both sides, right? So we have two carbons to look at. On this carbon, we are looking at what is the higher atomic number between the two substituents. And hopefully we can see that that's going to be the T-butyl, right? That's going to be this thing. This thing has the higher atomic number, right? Carbon has a higher atomic number than hydrogen. If we look on the right side of our alkene, we have on the bottom we have carbon bound to 3 H's. On the top we have carbon bound to another carbon. So therefore, just like with RNS, this would win. Ethyl group beats methyl group in RNS. And it does the same thing for here. And since they're on the same side, we call those the Z alkene. They're the same side of the alkene. Right? I hope I didn't give that to you the other way. Let's just double check real quick. But I know I should have given it to you the correct way. I think that's when we started talking about alkenes, yeah. So Yeah. So for Z things, higher priority groups are cis to each other. For E, the higher priority groups are trans to each other. So in this case, we have the higher priority groups on each one cis to each other, so it's Z. Cool. Got it. Okay. Kevin here making me doubt myself. So yeah, Z alkene. Anyways, if we take a look at our original molecule, we can just rotate it. We could rotate either the front or back carbon to get those two anti to each other. And so if we do that, we could rotate either one. Let's rotate the back carbon. If I rotate the back carbon, I'm going to need to rotate it 120 degrees, not 12 degrees. Let's try that again. 120 degrees, what is this way? Counterclockwise. Back carbon 22. You all thought all this rotation stuff was meaningless, huh? No, still useful. So if we rotate it, our T butyl group stays up. Actually, everything on the top stays. We now have our H on the left. We've got our methyl group down. We've got our ethyl group here. So when we eliminate, our base comes in. We eliminate. Notice the relationships. T-butyl and methyl are on opposite sides. They better be on opposite sides of your alkene. And that also tells you that the ethyl and the hydrogen need to be on opposite sides as well. So when we draw our alkene, we need to see, aha, we have our methyl group and our T-butyl group. Better be, I need to draw these out because we're doing a real structure. Our methyl group and T-butyl group are trans to each other. They're on the opposite sides. And our ethyl group and our hydrogen are on opposite sides. So that's the part that's important. So make sure a couple things. So the T-butyl and the hydrogen are on the same carbon, the front carbon. That's our front carbon right here. So make sure that your front carbon has the T-butyl and the hydrogen that's staying. And make sure that the other groups are in the correct positions relative to those. So the T-butyl and methyl are on opposite sides. They better be on opposite sides in your alkene. Hydrogen and ethyl on opposite sides, they should be opposite sides of the alkene. So we end up with Z. We can name this. Couple options. Couple options for naming it just for practice. Sounds so simple in theory, doesn't it? Guess what? It takes practice. Don't worry, your homework for this, that I haven't put up yet, is not nearly as long. Unless you would like me to go above 14 pages, uh, I'm not writing more problems for y'all. So, plus I think you're still recuperating from the last one. So, man, that was a killer. If it takes me a couple hours to do the key, I just can't imagine. Anyways, so looking at this, in either case, our highest priority group, if we use the blue numbers or the green numbers, is on the same carbons 3 and 4. So we're going to determine it by then putting our other locator groups as small as possible, therefore giving us the blue numbers will be our way to go for numbering this thing. So on carbon 2, carbon 1 has nothing, carbon 2 has methyl groups. Carbon 3 has a hydrogen, who cares? Carbon 4 has a methyl. Carbon 5 and 6 do not have anything. So we would say Z224 trimethyl, and what is this, hexene? Ideally, we could either say we could write it this way as well. I think the top one is technically like the preferred form, but I'm cool if you use the bottom one there. So just like with stereochemistry with R and S, we still put those at the start of the name in parentheses. In this case, we don't need a number because we only have one alkene, so it's understood that this is the Z alkene. If we had two, we would need to put the locator numbers. So you could say 3Z, that would be okay, but it's not necessary. So, okay. So that's how we would name this. So just for naming practice. Alrighty. Shall we do some more? I suppose the answer is yes, right? Let's see. Let's do a couple. Some from the book. Oops. So, just since you guys are here, I'll give you the option. Do you like doing it from wedge dash, or do you prefer doing it from a Newman projection? Or some other projection? Sawhorse, Fisher? Please don't make me do Fisher. But I would say for this, Newman and Sawhorse are I think, the easiest ways to do it. So to answer your question, I think Newman's the easiest because you can see very clearly how things are related, and that's where we have the most experience rotating them. I think so. Um, I'll go ahead and use Newman because for me that's the easiest. Or I mean, for me, I can do this with my eyes closed, but for you guys, I think Newman would be the easiest. So let's do that. So let's go ahead and do a Newman. So again, we're always looking at uh, our hydrogens and our, yeah, no need to brag, right? Uh, where our hydrogen is in this and where our other things are. So here we have no hydrogen on the right, wedge hydrogen on the left. Why do we have no hydrogen on the right, by the way? Don't forget a phenyl ring like that is going to be, it's got double bonds, right? So it's already got four. So no hydrogens there. If that was a cyclohexyl, then we would have a hydrogen there. But since it's a phenyl, we don't. So let's go ahead and do the Newman. The Newman you always want to draw between your leaving group carbon and your hydrogen. It doesn't matter which one you put front carbon and back carbon. I just predominantly put front carbon on the left. You can do either one. So I'm going to look at it this way. I think that would make the most sense. And so if we do that, let's take a look. We have an ethyl group up. We have a hydrogen on a wedge, which means it's on the right. We have a methyl group on the dash. On the back carbon, we have chlorine on the right. That's a wedge. Down, we have a phenyl group. And then we have a hydrogen on the dash. So we just need to rotate something. We can rotate our back carbon or front carbon. It doesn't matter. Doing this just allows us to see the relationships of our substituents to each other. That's what we're looking at here. In this case, let's see, last time I rotated the back carbon, let's rotate the front carbon this time. I want this H I need this hydrogen because the chlorine's on the back carbon. I need my front carbon hydrogen to be where the methyl is. So I'm going to rotate 120 degrees clockwise, giving us that carbon stays the same. And so now when we eliminate, here comes our base. We'll make our base green this time. Here it comes. Whoosh. Picks it out. Notice what we have opposite sides to each other. Methyl and phenyl are on opposite sides. And hydrogen and ethyl are on opposite sides. So as a result, put our phenyl group down, methyl group on the opposite, ethyl group over here, and then we have a hydrogen. So this would be our product. So I'm allowed to say E2, by the way. If I'm asking you to do this, I expect you to put a base there and maybe heat for the reaction conditions. So if I ask you, how do I go from here to here? You should tell me, oh, you'll just use the dimethylpyridine and heat, or triethylamine, or T-butoxide, or that crazy, even bigger one, the claw monster. Wherever it is. Where is the claw monster? There it is. This crazy claw thing. Bulky bases. Take your pick. Anyways, so there we go. So you'll need some sort of base and heat. If you don't use a bulky base, however, chances... Oh, I don't want to tell you about that. Never mind. We're good. So this will be our product. Any questions on that one? Let's look through the back of the book chapter here. Let's see if we've got some good problems. We'll do a couple more. Oh, ho, ho. Actually, this has a lot of choosing what to choose. Okay, let's see. Oh my gosh, there's so much here. Okay, here we go. Let's see what happens. I like this. Question 65 at the end of the chapter. And by, 7.65, okay. I thought I had read the number wrong. So we're going to be given a product we're told it has undergone an E2 reaction. Yes, retrosynthesis. So we need to evaluate some way of making this compound. And indeed, this process is called retrosynthesis or retrosynthetic analysis. We know with an E2 reaction, we form the double bond in between our leaving group and the hydrogen will be where our other one is. So we have a couple of options, right? We could have this. We could have our leaving group here, and we'll try to make this a little bit nicer. Or we could have our leaving group on the other side. And indeed, with this, we have multiple options, right? There's no reason why one would be preferred over the other, at least at this point in our education. Do we see how I've put the leaving group on either side? We could have it on the side that has on the carbon that has the T butyl, or we could have it on the other carbon. Either way. If we put it on the one with the T butyl group, we could assign stereochemistry to either one. We could say, well, how about this? We'll put that on a wedge, and we'll put a chlorine on the dash. Done. E2 gives us the product in question. However, if we look at the other case, if we want to put the leaving group on the other one, we need to make sure that we're able to get an anti-periplanar hydrogen to that. Interesting. I think it's easier to put it on the T butyl. So, but we'll see. The problem is with the leaving group on the other one, we have multiple options, right? We could say, well, if we have this on a wedge, do we need this on a dash? Or do we need them both on wedges? The most ugly wedge known to man. Or both on dashes. I mean, at that point, it doesn't matter, right? They'll react the same way. Which one's going to be better? I'll tell you right away, can't do this one. And unfortunately, if we eliminate, sorry, not unfortunately, but we'll see, there's an unfortunately. We do have an anti-periplanar hydrogen. These are cis to each other, cis 1, 2, the T butyl and the chlorine, which means one axial, one equatorial. So we can put our chlorine axially, that'll work. We have our T butyl equatorial, we have them able to eliminate, and we get our product. Ta-da! Ta-da! Is that right? Uh-oh. Also has some hydrogens down here. Oof, indeed. And if we eliminate, we end up getting a different product. I guess that's still on a wedge or whatever, but we could end up with a different product if we eliminate the purple hydrogens instead. So if we want our product to just have only this, if we want only one product, can't do it this way. Cannot use them on separate carbons. They have to be on the same one. That'll be the only way that we can get the desired product. And in fact, this red one, or the one that I've crossed out, will only give us this product. Well, the point is, if we eliminate either of these hydrogens, and I'm going to just draw them on wedges, either way we get the same product. Remember that if we eliminate the top one, we get that. If we eliminate the bottom purple one, these are the same molecule. These are equal to each other. Same molecule. Just rotated, flipped around. Same molecule. However, these two are not the same molecule. These two are not the same. Do we see that? They're not the same because the alkene is not in the same spot. The alkene is touching the T butyl on the right, not touching the T butyl on the left. Different molecules. However, on the left pair, those are the same molecule. So it doesn't matter which purple hydrogen we eliminate on the left molecule, we'll get the correct answer. And there's no hydrogens here So we don't have the possibility of getting a different product. Because that carbon is already full. It's already got 4 methyls, or 3 methyls in the cyclohexane, so no hydrogens on that one. Does that make sense, Shane? So, interestingly, if we wanted this one, if we wanted this product, we would use the crossed out red one. Not quite what you're asking. I see. Okay, because there's 2 options to eliminate versus 1 option to eliminate. Like you're thinking there's 1 hydrogen there versus 2 hydrogens there. Yes, indeed. I wouldn't worry about the number of hydrogens. That's more of a speed of reaction thing. But in terms of like the inability to get anything else, that's what we're looking at. So, for example, with the one that we crossed off with red, we're only ever going to get this product. Only this one. Actually, why am I doing that? If we eliminate this, we get, if we eliminate this red one, we only get that blue one. So this is a better choice for that one. For the one with the circled one in black here, for the desired product over there, this is the only way to for sure guarantee that we get it. So that's what we're looking at here. Let's do another one. We'll see if we can't get this to work a little better. Let's say I want this thing. We get it using E2. Apparently, I'm going into Neanderthal speech, but OChem does that to us, doesn't it? Well, again, let's look at it using 2 options. So we're going to get rid of our double bond. We're going to say, aha, well, we can put our leaving group here, or we can put it on the other side. Hopefully, we see that if we look at beta hydrogens, we have a crap ton on the left molecule, but on the right molecule, we only have 1 beta hydrogen. So that would be the better one to eliminate, right? Ta-da! Only 1 beta hydrogen. That's the only one that can be eliminated. That would give us our product. If we look at the one on the left, we have multiple products that could be formed. We could end up eliminating the bottom hydrogens or the top ones. Or we could get the product of interest. So as a result, because we have many options, but this one will only give us this one, we'll say that we'll use the one on the right. And note though, by the way, the one on the left, if we did want to try and force it to go Hoffman, we would use the bulkiest space possible. That would at least help. We may not get 100% of the product of interest, but we would help that out. So by using the super monstrous, here, let's do this one. Let's use this crazy base. Here we go. tricyclohexyl methoxide. Why not? Some crazy, crazy bulky base. Maybe you'll end up getting your Hoffman product. But still, you run the risk of making the side product. So the bulkier your base is, the more likely you are to get the Hoffman product. But it's just 100% easier if you only have one product that's available. So nothing else could be made through E2 with this right molecule. So we don't need this monster base, right? We could just go ahead and work with our plain old other bases. All right. How is that? Okay. Good. 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 Let's see. Easier to conceptualize. Yeah. All right. Let's do this. How about no, we already did that one. Are we ready to mix them all together? I think we are. Let's take a look at. Oh, actually, no. Let's do one more. Let's say we'll do a substitution one. I want this thing. I want this. And a couple ways to make it. We could say, aha, I'm going to take this thing and react it with. I'm going to actually adjust that. We always put this first. Both of these, theoretically, make this. Which one's better? Top one or bottom one? Hey, Kevin's already taken a look at this. So, absolutely. Absolutely. The second one is the better one. But let's look at why. So, remember when we're looking at substitutions, a lot of things we have to think about, right? We have to think about our nucleophile, to think about our solvent, we have to think about our substrate. In this case, we're not even given a solvent, who cares? Our nucleophiles are similar. They're both O minus of some sort. So they're nucleophiles. The T butoxide is a little bit harder to be a nucleophile, but there's no way we're going to get substitution on the top left molecule. This is a tertiary substrate. If we want to substitute here, and we want to do SN2, not going to work. Could work with SN1, could work with SN1, but we'd have to be real careful about our conditions because we don't want us to eliminate. If we have this, we have a primary substrate, or actually it's a methyl substrate. That's the best kind. If we compare the nucleophiles, this is the better nucleophile because it's smaller. Usually, your bulkier your nucleophiles get, the harder they are to be good nucleophiles. So this is a worse nucleophile. But I would still say that absolutely right. The second one, if you're going to do SN2, you'll only be able to do it from the second part, the second one. This one you'll end up doing SN1 with. If you want to do the top one, you've got to do it SN1. No other way. You'd have to have your iodine leave. You're going to have your sodium methoxide come over, and later, after you've made your carbocation, come over and boop, right on. So ideally, I would say the better one, because SN2 reactions are generally better controlled. We're not going to end up worrying about elimination, because with a methyl substrate, there's no beta hydrogens. There's only one carbon. So no elimination is possible here. The first one, if we try to do it SN1, it probably would work. It would be okay, but we run the risk of also eliminating. So we would end up with multiple products. So a lot of this stuff you just have to think about. You have to think about what's best here. Do we want to run the risk of elimination with a substitution? Never. We never do. So ideally, we want a nucleophile that's not basic. Or in this case, we have a substrate that is not possible to undergo elimination. So that'll work too. It's the same thing with that the craziness. Do you remember this T-butyl whatever bromide we had? You could potentially SN2 this, or you could E1 it. Or see, if we try to do SN2 conditions with this, you could make it work. Bad idea to use this as your nucleophile. But if it's SN2 conditions, it's not that bad, because there's no E2, no reaction. We have no beta hydrogens. However, so this all just depends, right? We can take the same substrate, treat it with the same reagent, and just kind of vary our conditions. If we do SN1, you end up getting your carbocation. Remember, we saw how it migrated the methyl group over? Or we saw E1 conditions. So, same substrate, same reactants can give you all these different products. Or no reaction at all. It depends what conditions you set for it. So, lots of things to keep in mind. If you SN2 this, you're safe using this nucleophile, by the way, because again, there's no possibility of E2. So you're good to go. Go ahead and do that SN2 style. In this case, I guess I didn't really need the wedge and dash because we have identical groups. It's not chiral. But if you did, remember SN2 inverts your stereochemistry. No possibility of E2 reaction here because we have no beta hydrogens. If we undergo a unimolecular process, we will migrate our carbocation by moving a methyl group over, and then we will either substitute or eliminate. So lots of different things to happen here. Let's take a moment to refresh our memories. So ideal, there are ways to help you guide yourself to one or the other. Ideally, with SN2, you want a strong nucleophile. Ooh, wow, that's ugly. Or strong base. You want actually, I'm gonna separate these because it's just gonna be too complicated to talk about both. You want a strong nucleophile that is hopefully non-basic, like sulfide or a cyanide. Those would be examples of strong non-basic nucleophiles, or even chloride, bromide, but you'd have to be kicking out something that's better than them. Those are non-basic nucleophiles. They're all very weak bases because they're stable, right? We have resonance stabilizing the nitrile. Um, we have the sulfur, chloride, and bromide because of their atom, right? Those can accommodate the negative charge pretty well. Strong nucleophile that's non-basic. You want a polar aprotic solvent. And you typically want to avoid, if you want to avoid elimination, if you have just the risk of the base being there, you want to make it as cold as possible because heat is going to help elimination. So typically that's what we're looking for. Your substrate, ideally, I'm going to move this over because your methyl group is technically a better substrate than a primary. Methyl substrate, a primary substrate, secondary substrate. That's it. Nothing else. And it's in this order. So these are your ideal conditions. Nice, strong nucleophile that's non-basic, a good polar aprotic solvent, cold temperature, and a methyl substrate. That'll be your best conditions. If you can't have a methyl, go for primary. If you don't have primary, you'll go secondary, but secondary is the limit. And secondary is already tough. Okay? That's our SN2 ideal. Ideally, E2, we want a strong base that's non-nucleophilic. Typically, we're looking at bulkier things then, or things that would just not make very good nucleophiles. So, like this nitrogen is so bulky, it's already not even close to an O minus. Um, let's see some pyridines, some sort of non-nucleophilic base, ideally a strong one. You want kind of higher temperatures, and you need the beta hydrogen that can be your substrate itself doesn't matter. You can have a primary, secondary, tertiary substrate. It matters if you have the beta hydrogen that can be made anti-periplanar. Make sure that if it's a ring, you're considering axial, that you need your leaving group axial to a hydrogen and anti. Um, you'd have to be able to rotate it. Some way of getting a beta hydrogen anti-periplanar to your leaving group. And then again, with these, you typically want a polar aprotic solvent. So those are your ideal conditions for E2. So in this case, we were not able to do E2 at all because we didn't have a beta hydrogen. So in this last example, we didn't see that as an option. And because it wasn't an option, we're free to use whatever nucleophile we want for SN2. We were able to use a basic nucleophile because There was no possibility of elimination under SN2 conditions. All right, unimolecular ones. SN1, you typically want a weak, non-basic nucleophile. Typically, that's the solvent. Your solvent, therefore, is going to be polar protic, and it's typically whatever you want to put in there. So if you want to put an alcohol, if you want to put um, a methoxy group, all these sorts of polar protic things typically are what you're substituting on. Your ideal substrate should be tertiary. I wouldn't recommend the others. Otherwise, you'll get rearrangements. And again, you want a lower temperature here for the substitution. For the elimination, it's the opposite side. For E1, you want a kind of, you can have a strong base here. Very often that might be sodium methoxide and methanol. You'll typically use both your conjugate base, or you'll use your solvent as your conjugate acid of your strong base. So methanol and sodium methoxide, ethanol and sodium ethoxide. Again, you want your solvent to be polar protic, and you want it to be probably the conjugate acid of your base. Substrate. Again, you ideally want this tertiary. You do need beta hydrogens, but remember, migrations happen, so you probably will end up with all sorts of stuff. You also need some beta hydrogen. So it depends if you're eliminating, if your leaving group leaves and there's no beta hydrogens, you're probably not going to eliminate. But if it leaves and migrates, maybe you do have new um, beta hydrogens. So it just depends. You have to have hydrogens beta to where your carbocation is. So just keep that in mind. And then the last thing, you typically want higher temperatures for eliminations. So that'll help guide it that way. Wow. Cool. So we have kind of our four conditions. There's one last little bit that I want to talk about before we end today. So these are the conditions that you'll want to practice with, because you see that the same good, the mush has happened. The same substrate here did three different things in three different conditions. If we wanted to force one of them, if we wanted to force this to go SN2, we would probably want to make sure we have a polar aprotic solvent, like acetone, like acetonitrile, DMSO, something like that. If we want this to go SN1, ideally we would not even use the sodium methoxide. We would just use methanol at low temperature. That would be probably the best way to force this to go to get that product. To get this one, ideally we'll put the base with its conjugate acid, heat it up, and we'll very likely get our E1 product. So depending the conditions you use, your solvent, your temperature, will determine what your major product will be. Unfortunately, with this, they've got a lot of options. So um, it's potential that all three things would happen. E2, of course, would not happen in any circumstance. So, but you could have SN2, you could have E1, you could have SN1 all happening at the same time. So look at your conditions, choose your conditions so that they are most appropriate for the reaction you want to happen. So in reality, yes, you might end up with a mixture of products. But on paper, we can just say, aha, this is the major product. Because I've said I'm using this polar aprotic solvent and there's no possibility of E2, I'm going to go ahead and just go ahead and do this. So, all right, think about this. Write these down, commit them to your memory, perhaps. Or make nice cards of all these different reaction types. Okay, one more thing. We've talked about alkyl halides as leaving groups. Let's talk about oxygens. Let's talk about OH as a leaving group. If you want to do E1 or SN1 with a hydroxy around, generally elimination is easier. All you need to do is treat this with some sulfuric acid, and you will eliminate via an E1 type reaction. Because in the presence of the acid, you will protonate your oxygen. Now we have a very good leaving group. OH is a terrible leaving group. However, OH2 plus, aka water, is a great leaving group. Ta-da! It leaves. We get our carbocation could migrate as necessary. And then, in fact, just some more water. That same water could come right back, and it's going to go ahead and eliminate. I didn't show the step of the protonation, but remember H2SO4, we could just say that's H3O plus. Oh my gosh. Doing that, we end up now with our protonated alcohol, so I'll show that step. And then we end up with our product. So in an E1 type pathway, you can just add some acid and heat it, and you'll end up eliminating a hydroxy group. So easy enough, right? Protonate the hydroxy, it becomes OH2 plus, great leaving group. It comes in and leaves, and then it can come back and take off the hydrogen and eliminate to get your product. If you want it as a leaving group for a bimolecular reaction, this could happen, by the way, if you want to. I mean, there's no point in substituting this because it would just be substituted with OH again, so never mind. OH is a terrible leaving group, but we can turn it into a great leaving group by using what's called toluene sulfonyl chloride, or TSCl, also said tosyl chloride. This thing can turn an OH into a great leaving group for SN2 or E2 reactions. What happens I'm going to just do this in one step. There's really multiple steps that happen here, but I don't really need you to focus on this mechanism. You end up losing your chlorine. You have a base coming in. Usually that's pyridine. Comes in, and you end up now getting this thing. This is a great leaving group because it can resonate like crazy once you have it go away. You can have, aha, here is your, here's our nucleophile. Comes in, kicks it out. We end up doing SN2 here. And we lose, as the byproduct, this guy. This is why it's such a good leaving group. It can resonate onto those oxygens. You could resonate into the benzene ring. This is super resonance stabilized. So what you can do, if you want to do an SN2 reaction and you have an OH, I'm going to just show this to you right now in one step. Like, boom, here's our OH. Got some stereochemistry on it. If you put also chloride and pyridine in there, you end up with this OTS. Instead of drawing the whole thing, people abbreviate this OTS. And now you can treat that with your nucleophile. And why don't we use the acetonitrile this time as our solvent? We end up doing a plain old SN2 reaction. So you can use this set of reagents. This transforms a bad leaving group to a great one. And notice your stereochemistry is the same. If your oxygen was on a wedge before, it's still on a wedge in your product. So if you're going to tosylate your alcohol, you can do that, and now it's a great leaving group, and now you can do an SN2 reaction or an E2 reaction as you see fit. So it's a way of um, making this work out for you. So we'll continue. There's not much more to do with this. We'll practice. And yeah, we'll go from there. All right, so I'll post your homework later and we'll go from there. So, all right. Take care, everyone. Enjoy your rest of your day.